Hello, this is our video for Lab 4, and I will be going over the sim that we used for our data. First off, I would like to make it known that Dr. Osbey himself cleared the fact that I'm using StarCCM. He said he does not care as long as it gives him the results he wants. So, yes, that is why I'm using Star. I prefer it over ANSYS, and he said it was fine. So now that that's out of the way, I'll go over what I've done. So as you can see here, this is the velocity contour. These I will explain, although these don't affect the test section at all. It's just a consequence of a really refined mesh, as you can see here. This is an incredibly refined mesh. Sadly, I'm not really, at least I'm not aware of a way to specifically pick this boundary layer. It kind of, the settings I mess with the prism layers, which are right here, prism layer controls, which control this section here, which is the really, really refined kind of rectangular cells. That's the prism layer, and those kind of just apply to all the surfaces. So because this is incredibly refined, you're getting these beautiful but strange kind of wake separation region here, where it's very obvious that it's separating and it's causing these really funky looking wakes. But these are not affecting at all kind of what's going on here in the test section. It's basically unaffected. Because of the really, really refined mesh that I have, you can see we have a very pretty and clean velocity gradient here for the boundary layer, which gives us very good results. These three lines are just line probes. You can see they are, I'll show you them here. They are just 1 point, 2 points, and you choose how many what the resolution is, how many points in between, and they're all the same exact length, and they have the same amount of points, so they give the exact same data essentially in terms of data points when we put this in Excel. So you can see how clean this kind of velocity gradient is, and that will directly result in very clean plots here. So these two, the 8 centimeter and 16 centimeter, align basically perfectly with what the Blasius theoretical solution is, and I'll show that really quick in a second, really quickly in a second on the Excel graph we have. But the 0.2 centimeters, you can see it actually overshoots right here, because we have 55 hertz for the fan speed, using the equation we got in lab 1. It basically made the free stream essentially 11.2. You can see it actually still hasn't really fully merged. This bump where it overshoots the free stream and then kind of goes back towards it seems to actually be due to the fact that there seems to be a low pressure region at the leading edge. You can see it right here, and that causes an acceleration of the velocity over the front of the plate at the very edge, at the very tip. That basically goes away for these 2 points, which is why they're so clean, and they basically align perfectly with what we theorize. But due to this kind of acceleration, what ends up happening is that it kind of accelerates, which causes an extra bump where it overshoots, and then it's not really long enough where it would reach the free stream. It's still kind of in this high velocity pocket. But you can see here, this actually aligns very closely with Blasius, but then it goes past when it should be kind of curving out here and then going to free stream. It shoots past and then rebounds. But yeah, you can also see that the du dy, so the velocity gradient, is incredibly aggressive for the 0.2, which aligns with our understanding of the theory behind it, because that will cause an increased shear force on the surface, which will begin to go down as this velocity gradient starts to lift and grow as the boundary layer grows, and that will cause less severe du dy, which will cause lower and lower shear forces, which we can see here. This is the wake region. The plate ends here. It kind of freaks out. I'm not really sure it knows what's going on there, but this is what we're looking at, which is from leading edge to trailing edge. It grows here. This is due to, I believe, the acceleration at the leading edge, but this is basically what we'd imagine with theory, with just the theory aspect of it, where it goes from a high shear force, starts decreasing, and then increases a little bit at the end, and that's due to the fact that it starts to shrink back down as it gets sucked in by the wake. You can see it starts growing, and out here it starts to decrease a little bit, and it shrinks down, and then it gets sucked into the wake region. So this aligns, as of right now with the data, aligns very well with the theory. These look basically identical to what Blasius tells us it should be. And here you can just see my plots. I really only have 4 plots here. Shear force, which I get from doing a accumulated force table, and then I just choose the boundary layer for the plate and the parts, and then I just dump that into an XY plot for shear force, and then that's what I get here. And these 3 are just me dumping the line probes into here as well. This is where I got my free stream velocity value. You can see right here. Free stream velocity value, it gives us when if it were to report it. I don't know why it's not reporting right now, but it has reported it to me. It's around 11.2, 11.3. That's from the frequency we were given in the lab, which is 55 hertz. So yeah, that is about it. That is all I have in terms of the lab sim. I can really quickly go over the models I used. Here I'll show you the models I used in case you wanted to know. I used equilibrium air, gas, laminar, which is what we're told to do in the lab. It would be very low Reynolds numbers. Does not reach the 500,000 necessary for turbulent flow. Steady, obviously 2-dimensional. Segregated fluid enthalpy, real gas. I could have done ideal gas, that would have essentially given me the same results, but why not? Segregated flow, and the reference values I used, that's actually here at the inlet. Velocity specification, physics values, velocity magnitude 2.8 meters per second, which is what I get from using the equation for 55 hertz. Yes, so that's about it. That's all I really have in terms of the sim. And thank you for taking the time to look at this if you actually did.